The Fermi 1 reactor represented the first serious attempt to demonstrate commercial fast breeder technology in the United States, embodying design philosophies that would prove both technically sound and diagnostically treacherous. As a 200 MWF, 61 MWE liquid metal fast breeder reactor located on the western shore of Lake Erie near Detroit, Michigan, the facility operated on fundamentally different principles from the light water reactors that would dominate commercial nuclear power. The reactor achieved first criticality in August 1963 and began power operations in August 1966, marking the culmination of nearly a decade of fast reactor development by Atomic Power Development Associates and the Power Reactor Development Company. The reactor's core contained 105 fuel assemblies arranged in a cylindrical configuration within a sodium-cooled vessel, each assembly housing 140 metallic uranium fuel pins with 0.158-inch outer diameter and 31-inch height, positioned in a square lattice arrangement. This geometric configuration represented the fundamental compromise of fast reactor design, achieving the tight lattice spacing necessary for optimal neutron economy while maintaining adequate coolant flow paths for heat removal. The fuel assemblies were supported by a core structure that directed liquid sodium upward through each assembly, with individual outlet thermocouples monitoring the thermal performance of each fuel bundle. The sodium coolant system formed the technological heart of the reactor's thermal management philosophy. Operating with inlet temperatures of 288 degrees Celsius and outlet temperatures of 427 degrees Celsius at a system pressure of 120 psia. Unlike water-cooled reactors, where steam generation provided obvious visual and audible indicators of heat removal effectiveness, the liquid metal system offered no phase change phenomena visible to operators. The single-phase sodium remained liquid throughout the temperature range, providing excellent heat transfer characteristics, but eliminating the intuitive diagnostic cues that operators in conventional power plants could rely upon to assess system performance. This fundamental characteristic of liquid metal cooling created the first critical assumption embedded in the reactor's design philosophy: that adequate thermal monitoring could be achieved through indirect measurement of coolant temperatures at fuel assembly outlets, without direct verification of coolant flow rates or visual confirmation of flow distribution patterns. The assumption appeared technically sound, supported by extensive thermal analysis demonstrating that outlet thermocouple readings would provide reliable indication of heat removal effectiveness under all anticipated operating conditions. The reactor's instrumentation architecture reflected this design philosophy through its emphasis on temperature measurement as the primary diagnostic tool for core thermal conditions. Each fuel assembly was equipped with an outlet thermocouple designed to detect temperature variations that might indicate changes in power generation or cooling effectiveness within that specific assembly. The instrumentation system was designed to provide operators with quantitative temperature data from all 105 fuel assemblies, creating what appeared to be comprehensive thermal monitoring coverage of the entire reactor core. However, the instrumentation logic contained a subtle but critical limitation. It measured the effects of thermal conditions rather than their causes. Thermocouple readings could indicate that fuel assembly outlet temperatures were elevated, but they provided no direct information about whether temperature increases resulted from increased power generation, reduced coolant flow, or changes in inlet temperature. The diagnostic framework assumed that operators could distinguish between these different causes through correlation with other plant parameters, such as neutron flux measurements and reactor power level indications. The control room interface design supported this diagnostic approach by presenting thermocouple readings in formats that emphasized comparative analysis between fuel assemblies and trending of individual assembly performance over time. Operators were trained to interpret temperature patterns across the core, identifying assemblies that operated consistently above or below average temperatures and investigating the causes of significant temperature variations. The human-machine interface assumed that thermal problems would manifest as clear, unambiguous temperature increases that could be traced to specific causes through systematic analysis of multiple information sources. The reactor's safety philosophy incorporated multiple independent barriers designed to prevent core damage through defense-in-depth principles that had proven effective in earlier reactor designs. The primary barrier consisted of maintaining adequate coolant flow through design margins and operational limits that ensured fuel temperatures remained within acceptable bounds under all normal and anticipated transient conditions. Secondary protection included automatic reactor trip systems triggered by high temperatures, neutron flux anomalies, or loss of coolant circulation. The ultimate barrier consisted of containment systems designed to prevent release of radioactive materials to the environment, even in the unlikely event that fuel damage occurred. This safety architecture reflected the engineering confidence typical of 1960s nuclear technology development. Based on systematic analysis of anticipated failure modes and the implementation of multiple independent protection systems to address each identified threat. The approach had proven successful in earlier reactor designs and represented the state-of-the-art in nuclear safety philosophy. However, the effectiveness of defense-in-depth depended critically on the ability to detect challenges to each barrier before they progressed to conditions that might overwhelm subsequent protection layers. The reactor design incorporated an assumption that would prove problematic during the subsequent operational period, that the reactor's inlet plenum would remain free of debris that could obstruct coolant flow to individual fuel assemblies throughout the reactor's operational lifetime. This assumption appeared reasonable given the closed nature of the primary coolant system and the absence of obvious debris sources within the reactor vessel. The original design analysis focused on preventing coolant leakage, maintaining pump performance, and ensuring adequate heat removal under various power and flow conditions, but gave limited attention to the possibility that reactor internal components might break loose and create flow blockages. During the reactor's construction phase, 6 small zircaloy deflector plates were added to the reactor design to optimize sodium flow distribution through the core. These plates, measuring approximately 16 inches by 8 inches, were installed at the bottom of the reactor vessel in the inlet plenum area, positioned to direct incoming sodium flow upward through the fuel assemblies rather than allowing turbulent mixing patterns that might reduce cooling efficiency. The modification represented standard engineering practice for reactor optimization, intended to ensure uniform flow distribution and eliminate potential thermal hotspots that could develop from uneven coolant circulation. The deflector plates were secured to reactor internal structures through mechanical attachments designed to withstand the thermal and hydraulic conditions within the sodium-filled reactor vessel. The attachment system was analyzed for normal operating stresses including thermal expansion, flow-induced vibration, and pressure differentials across the plates. Under design conditions, the plates were expected to remain securely mounted throughout the reactor's operational life, performing their flow distribution function without requiring maintenance or replacement. However, the addition of these deflector plates occurred late in the reactor's design process, representing a modification to optimize performance rather than an original design feature. This timing meant that the plates were not subjected to the same comprehensive design review and failure analysis procedures that had been applied to other reactor internals during the initial design phase. The modification process followed established engineering procedures for plant improvements, but the scope of analysis focused on the plate's intended function rather than comprehensive evaluation of their potential failure modes and consequences. The deflector plate installation created a condition that would later prove significant. The presence of relatively large metallic components within the reactor's inlet plenum that were subject to thermal cycling, flow-induced forces, and potential fatigue mechanisms during reactor operation. The plate's location at the base of the reactor core placed them in the most hydraulically active region of the primary system, where they would experience the full range of flow transients associated with reactor startup, shutdown, and power change operations. The reactor's operational procedures reflected the assumption that internal components would remain stable throughout the reactor's service life, with no specific provisions for monitoring the condition of deflector plates or other internal structures that were not accessible for direct inspection during normal maintenance periods. The procedures emphasized monitoring of accessible components such as pumps, heat exchangers, and instrumentation systems, while assuming that reactor internals would perform their intended functions without degradation or failure. The diagnostic capabilities available to reactor operators were optimized for detecting and responding to anticipated failure modes such as loss of primary coolant circulation, steam generator problems, or control system malfunctions. The procedures and training programs prepared operators to recognize and respond to thermal anomalies that might result from these well-understood problems, but did not specifically address the possibility of progressive flow blockage caused by debris migration within the primary system. The reactor's alarm systems were designed around absolute parameter thresholds rather than pattern recognition or trend analysis capabilities, reflecting the technological limitations of 1960s control and instrumentation systems. Individual fuel assembly thermocouples would trigger alarms when temperatures exceeded predetermined limits, but the alarm logic provided no capability for detecting subtle temperature patterns that might indicate developing flow problems before they reached alarm thresholds. Operators were expected to perform this pattern recognition manually, using their training and experience to identify emerging trends in the temperature data. The institutional environment surrounding the Fermi 1 reactor created additional pressures that would influence operational decision-making during challenging situations. As a demonstration reactor designed to prove the technical and economic feasibility of fast breeder technology, the plant operated under intense scrutiny from the Atomic Energy Commission, nuclear industry observers, and public critics who questioned the safety and viability of liquid metal reactor concepts. This environment created institutional incentives to demonstrate successful operation and minimize the significance of operational anomalies that might be interpreted as evidence of fundamental design problems. The reactor had experienced various minor operational challenges during its initial operating period, including neutron flux fluctuations, temperature variations between fuel assemblies, and occasional control system anomalies. These problems were generally attributed to the expected difficulties of operating an experimental reactor design, with engineering efforts focused on developing procedural workarounds rather than conducting comprehensive investigations into root causes. This approach reflected the practical realities of operating a complex experimental system while maintaining operational schedules and demonstrating reactor performance. The reactor's information architecture created a sophisticated but ultimately incomplete picture of system conditions for operators and engineering personnel. The wealth of temperature, pressure, flow, and neutron flux data provided detailed quantitative information about reactor performance, but this information was filtered through assumptions about system behavior that had been embedded in the design process. When these assumptions proved invalid under actual operating conditions, the same instrumentation that provided confidence during normal operation could become misleading during off-normal situations. The stage was set for a failure mode that would challenge every aspect of the reactor's diagnostic and safety systems while remaining invisible to the monitoring capabilities that operators depended upon to understand and control the reactor. The precise instrumentation, comprehensive procedures, and multiple safety barriers that had been implemented to ensure safe operation would prove adequate for their intended purposes, but insufficient for detecting and preventing a failure mode that fell outside the conceptual framework underlying the reactor's design philosophy. The conditions that enabled the Fermi 1 fuel damage were established through a convergence of design modifications, operational practices, and human factors that individually appeared reasonable but collectively created a pathway to system failure. These latent conditions existed within the reactor system for months before the October 1966 incident, invisible to operators and engineers who were managing the day-to-day challenges of operating an experimental fast breeder reactor under intense technical and political scrutiny. The most significant latent condition originated from the deflector plate modification process itself, which had introduced components into the reactor system without subjecting them to the rigorous failure mode analysis applied to original design elements. The 6 zircaloy plates installed in the reactor's inlet plenum represented a seemingly minor optimization intended to improve coolant flow distribution, but their addition created mechanical components subject to thermal cycling, flow-induced vibration, and potential fatigue mechanisms that had not been comprehensively analyzed during the modification review process. The deflector plates were positioned in the reactor's inlet plenum directly below the core support structure, where they experienced the full range of thermal transients associated with reactor operation. During startup operations, the plates were subjected to rapid temperature increases as sodium temperatures rose from near ambient conditions to operating levels exceeding 280 degrees Celsius. Shutdown operations imposed the reverse thermal cycle, with rapid cooling that created thermal contraction stresses in both the plates and their mounting hardware. These thermal cycles occurred dozens of times during the reactor's operational history, creating cumulative fatigue loading that was not explicitly considered during the modification analysis. The hydraulic environment surrounding the deflector plates imposed additional stresses that varied with reactor operating conditions. During high-power operation, sodium flow velocities through the inlet plenum created dynamic loading on the plates from turbulent flow patterns and pressure fluctuations associated with pump operation. The plates were also subjected to differential pressures across their surfaces as sodium flow was redirected upward through the fuel assemblies, creating bending moments in the plate structures and their mounting attachments. The mounting system for the deflector plates consisted of mechanical attachments designed to secure the plates to existing reactor internal structures without requiring major modifications to the reactor vessel or core support systems. The attachment design represented a compromise between the need for secure mounting and the practical constraints of installing the plates within the confined space of the reactor's inlet plenum. The mounting hardware was fabricated from materials compatible with the high-temperature sodium environment, but the specific attachment details were not subjected to the same level of analysis and testing applied to original reactor components. The reactor's maintenance and inspection procedures contained a critical gap regarding the deflector plates and other internal reactor components that were not accessible during routine maintenance outages. Visual inspection of reactor internals was impossible during operation due to the opacity of liquid sodium, and the plate's location within the inlet plenum made them inaccessible during normal shutdown periods without major disassembly of reactor systems. This meant that the condition of the plates could not be verified through normal maintenance activities, creating a blind spot in the reactor's component surveillance program. The plant's quality assurance procedures for design modifications followed standard industry practices for the 1960s, emphasizing compliance with design specifications and installation procedures rather than comprehensive long-term reliability analysis. The deflector plate modification was implemented through established change control processes, but these procedures focused primarily on ensuring that the modification would perform its intended function rather than analyzing all potential failure modes and their consequences. The modification was classified as a performance optimization rather than a safety-related change, which reduced the level of analysis and review required under existing procedures. The reactor's operational history during the months preceding the October 1966 incident provided subtle indications that conditions within the core were not entirely consistent with design expectations. But these symptoms were not recognized as evidence of developing mechanical problems. Fuel assembly outlet thermocouples had been indicating temperature variations that did not correlate clearly with predicted power distribution patterns or control rod positions. Some assemblies consistently operated at temperatures higher than their neighbors, while others showed temperatures below expected values based on neutron flux measurements. These temperature anomalies were initially attributed to thermocouple calibration drift, instrumentation problems, or minor variations in fuel enrichment between assemblies. The variations were typically modest, ranging from 10 to 30 degrees Celsius from expected values, which fell within the range that thermal analysis had shown to be acceptable for continued operation. When suspect assemblies were relocated to different core positions during refueling operations, the temperature anomalies remained associated with specific core locations rather than following the moved assemblies, suggesting that the cause was related to flow patterns rather than fuel characteristics. The pattern of temperature readings proved particularly puzzling because the anomalies appeared and disappeared seemingly at random, with affected assemblies sometimes returning to normal temperature ranges without any obvious explanation. This intermittent behavior reinforced the interpretation that the problems were instrumentation-related rather than indicative of systematic mechanical issues within the reactor core. The temporary nature of many temperature excursions suggested transient conditions that resolve themselves, supporting the assumption that no permanent changes in reactor configuration were occurring. The reactor's alarm system design represented another latent condition that would influence operator response during the eventual emergency. The alarm logic was based on absolute parameter thresholds determined from safety analysis calculations, with individual alarms triggered when specific measurements exceeded predetermined limits. This approach reflected the technological capabilities of analog instrumentation and relay-based control systems available in the 1960s, which could monitor individual parameters but lacked the computational capability for complex pattern recognition or trend analysis. The alarm system could detect when fuel assembly outlet temperatures exceeded safety limits, but it provided no capability for recognizing subtle patterns of temperature changes that might indicate developing problems before they reached alarm thresholds. The system was designed to alert operators to conditions that required immediate attention, not to provide early warning of gradually developing problems that might escalate to serious conditions over extended periods. Operators were expected to perform pattern recognition and trend analysis manually, using their training and experience, to identify emerging problems from the raw temperature data. The reactor's operating procedures included protocols for responding to temperature anomalies in fuel assemblies, but these procedures were developed based on anticipated failure modes such as loss of primary coolant circulation, control rod malfunctions, or steam generator problems. The procedures assumed that thermal problems would manifest as clear, unambiguous temperature increases that could be traced to specific causes through systematic analysis of reactor operating parameters. The possibility of partial flow blockage caused by debris migration was not specifically addressed in the emergency operating procedures available to reactor operators. Training programs for reactor operators emphasize the importance of monitoring fuel assembly outlet temperatures as the primary means of detecting core thermal problems, but the training scenarios were based on well-understood transient conditions rather than novel failure modes involving progressive flow blockage. Operators learned to interpret temperature patterns across the core and take appropriate corrective actions based on the magnitude and distribution of temperature anomalies, but they were not prepared to recognize the subtle intermittent temperature variations that might indicate debris-induced flow problems. The institutional environment surrounding the Fermi 1 reactor created additional latent conditions that influenced decision-making during operational challenges. As a demonstration plant operating under intense scrutiny from regulators, industry observers, and nuclear critics, the facility faced pressure to demonstrate successful operation while minimizing the significance of operational anomalies that might be interpreted as evidence of fundamental design problems. This environment created incentives to attribute operational difficulties to well-understood, easily correctable problems rather than acknowledging the possibility of novel failure modes that might require extensive investigation. The reactor had experienced various operational challenges during its initial operating period, including neutron flux fluctuations, control system anomalies, and temperature variations between fuel assemblies. These problems were generally managed through procedural modifications and operational workarounds, rather than comprehensive root cause investigations that might have revealed underlying systematic issues. The approach reflected practical considerations of maintaining operational schedules and demonstrating reactor performance, but it also meant that patterns of symptoms indicating developing mechanical problems might not be recognized and investigated. The relationship between reactor operators and plant engineering staff created another layer of complexity in problem diagnosis and response. Operators were trained to follow established procedures and consult engineering personnel when conditions exceeded their training experience. But the engineers were often focused on specific technical challenges related to reactor physics, thermal analysis, or component performance rather than integrated system operation. This division of responsibility could result in communication gaps where operational symptoms might not be effectively communicated to engineering personnel with the expertise to recognize their significance. The reactor's instrumentation system contained inherent limitations that created opportunities for misinterpretation of plant conditions under off-normal circumstances. The thermocouple systems provided accurate measurements of bulk coolant temperatures at fuel assembly outlets, but they could not distinguish between temperature increases caused by power variations and those resulting from flow reductions. Under normal operating conditions, this limitation was not significant because power and flow changes typically occurred together in predictable patterns. However, under conditions of partial flow blockage, temperature measurements could become misleading because reduced flow rates would cause higher temperatures even with unchanged power generation rates. The reactor's neutron flux monitoring system provided complementary information about core conditions, but the relationship between neutron flux patterns and thermal conditions was complex and dependent on factors such as control rod positioning, fuel loading patterns, and reactor operating history. Operators were trained to correlate neutron flux and temperature measurements under normal operating conditions, but this correlation could become unreliable during transient situations where localized flow blockages might create thermal conditions that did not correspond to neutron flux patterns. The physical layout of the reactor core created geometric constraints that limited options for managing flow distribution problems, even if they were detected early. The tight lattice spacing between fuel assemblies optimized for neutron economy meant that blockage of flow to one assembly could not be compensated by increasing flow to adjacent assemblies. The core design provided excellent performance under normal conditions but offered limited flexibility for managing off-normal flow distributions that might develop during operational transients. The sodium coolant system's operating characteristics contributed to the difficulty of detecting flow problems through available instrumentation. Unlike water-cooled reactors, where changes in flow conditions might create detectable changes in system pressure, pump performance, or heat exchanger operation, the single-phase sodium system provided few indirect indicators of flow distribution changes within the reactor core. The primary circulation system could maintain normal overall flow rates and system pressures even if flow to individual fuel assemblies was significantly reduced by local blockages. These latent conditions created a situation where a relatively minor mechanical failure could initiate a sequence of events that would challenge both the reactor's safety systems and the operator's diagnostic capabilities. The failure mechanism was not the result of any single design defect or operational error, but rather emerged from the interaction of multiple conditions that individually appeared acceptable, but collectively created vulnerability to failure modes that had not been adequately anticipated during the design process. The reactor system had evolved into a configuration where sophisticated instrumentation provided detailed quantitative data about system performance while remaining unable to detect or diagnose the specific type of mechanical failure that posed the greatest threat to fuel integrity. The same design optimizations that had improved reactor performance under normal conditions had also created diagnostic blind spots that would prove critical when abnormal conditions developed within the reactor core. The initiating event of the Fermi 1 fuel damage began several days before October 5, 1966, with the mechanical failure of one of the 6 zircaloy deflector plates that had been installed in the reactor's inlet plenum during construction. The failure occurred during normal reactor operation, when cumulative thermal cycling and flow-induced vibration caused fatigue cracking in the weld attachments securing one plate to the reactor's internal support structure. The plate broke loose from its mounting position and became a piece of debris within the sodium coolant circulation system, setting in motion a sequence of events that would remain undetectable to operators until irreversible fuel damage had occurred. The loose deflector plate measured approximately 16 inches in length and 8 inches in width, with a thickness of about 1/4 inch and constructed of zircaloy 2 material. The plate retained its structural integrity after breaking loose, maintaining sufficient mass and rigidity to resist deformation by sodium flow while being transported throughout the reactor's primary system. The plate's dimensions were significant because it was large enough to create substantial flow blockage when positioned against fuel assembly inlet nozzles, but small enough to be mobile within the sodium circulation system under the influence of varying flow patterns. The hydraulic forces within the reactor's primary coolant system caused the loose plate to migrate through the inlet plenum according to flow patterns that varied with reactor power level, primary pump operation, and thermal conditions within the reactor vessel. During periods of high sodium flow associated with higher power operation, the plate would be swept along with the coolant stream, potentially moving between different locations within the inlet plenum. When flow rates decreased during power reductions or transient operations, the plate would settle in areas of lower velocity where it might come to rest against fuel assembly inlet structures or other reactor internals. This debris migration pattern created intermittent flow blockage conditions that manifested as seemingly random temperature variations in the affected fuel assemblies. When the plate lodged against a fuel assembly inlet nozzle, it would partially or completely obstruct coolant flow through that assembly, causing outlet temperatures to increase even though power generation rates remained constant. The temperature increases reflected the basic physics of heat transfer. With reduced coolant flow available for heat removal, the same heat generation rate would result in higher coolant temperatures at the assembly outlet. When hydraulic forces subsequently moved the plate away from a blocked assembly, normal coolant flow would be restored and temperatures would decrease toward normal values. This intermittent behavior created a pattern of temperature fluctuations that did not correspond to any anticipated reactor operating condition or failure mode covered in operator training programs. The seemingly random nature of the temperature variations reinforced the interpretation that they were caused by instrumentation problems rather than systematic, mechanical changes within the reactor core. The reactor had been experiencing these temperature anomalies for several weeks prior to October 5th, but the intermittent nature of the symptoms and their modest magnitude had led operators and engineering personnel to attribute them to thermocouple drift, electrical interference, or minor variations in fuel assembly characteristics. The temperature increases typically ranged from 10 to 30 degrees Celsius above normal values, which fell within the operational margins that thermal analysis had shown to be acceptable for continued reactor operation. During the days immediately preceding October 5th, reactor operators observed an increasing frequency of temperature anomalies affecting various fuel assemblies throughout the core, but the pattern did not suggest a systematic problem requiring immediate corrective action. The temperature variations appeared to affect different assemblies at different times, with some assemblies returning to normal readings while others began showing elevated temperatures. This pattern was consistent with a mobile debris object that was moving between different positions within the reactor core. But this explanation was not considered because debris generation and transport were not anticipated failure modes under the reactor's design assumptions. On October 5th, reactor operators began a planned power change operation as part of the ongoing power escalation testing program designed to demonstrate the reactor's performance characteristics at progressively higher power levels. The reactor had been operating successfully at 100 MWF, and the plan called for a temporary reduction to establish stable conditions before proceeding to even higher power levels in subsequent testing phases. The power reduction was considered a routine operational evolution rather than a response to any specific, technical concerns about reactor performance. At approximately 3 p.m. on October 5th, with the reactor operating at 20 MWF under manual control, operators observed the first clear indication that reactor conditions were departing from normal expectations in ways that could not be easily explained by familiar failure modes. Neutron flux instrumentation began displaying erratic readings that suggested rapid fluctuations in reactor power level. Even though control rod positions had not been changed and no obvious external cause for power variations was apparent to the operators. The neutron flux anomalies initially appeared consistent with electrical problems in the instrumentation system, based on similar symptoms that had been observed and successfully resolved during previous operating periods. Electrical interference, loose connections, or component drift in neutron detection systems were well understood problems that could create the appearance of power fluctuations without actual changes in reactor neutron population. The operator's initial response followed established procedures for managing instrumentation anomalies by switching from automatic to manual control to eliminate the possibility that control system responses to spurious signals might cause actual power changes. However, the neutron flux fluctuations were not caused by instrumentation problems, but by actual changes in reactor power resulting from the physical movement of the loose deflector plate within the inlet plenum. As the plate shifted position, it alternately blocked and unblocked coolant flow to specific fuel assemblies, creating thermal conditions that caused localized changes in fuel temperature and reactivity. When coolant flow was reduced, fuel temperatures increased beyond normal operating ranges, causing thermal expansion of fuel materials and changes in neutron absorption characteristics that affected the reactor's neutron multiplication factor. The reactor's automatic control systems detected these reactivity changes through neutron flux instrumentation and responded by adjusting control rod positions to maintain the desired power level. When fuel heating caused positive reactivity insertion, the control system withdrew control rods to compensate for the reactivity change and maintain stable power operation. These control system responses were appropriate based on the neutron flux signals the system received, but they were compensating for the consequences of fuel damage rather than normal reactivity effects associated with temperature or power changes. When the erratic neutron flux readings temporarily disappeared, operators restored automatic control, assuming that the electrical problem had been resolved. This decision followed standard operating practices for managing transient instrumentation problems and reflected the operator's understanding of reactor behavior based on their training and experience. However, the temporary stabilization of neutron flux readings actually indicated that the debris had moved to a position where it was not creating significant flow blockage, allowing thermal conditions to normalize temporarily. At 3:05 p.m., with reactor power at 27 MW, the neutron flux anomalies returned with greater intensity than before. Operators noted that control rods had withdrawn farther from the core than normal to maintain the desired power level, indicating that the reactor required additional positive reactivity to achieve criticality. This condition suggested that something was affecting the core's neutron multiplication characteristics, but the specific mechanism was not immediately apparent to operators who were focused on maintaining stable power operation according to established procedures. The thermocouple readings during this period provided the first unambiguous indication that serious thermal problems were developing within specific fuel assemblies. Two assemblies showed outlet coolant temperatures of 370 degrees Celsius and 380 degrees Celsius, significantly higher than the bulk coolant temperature of 315 degrees Celsius and well above the normal temperature variations that had been observed during previous reactor operation. These temperature readings represented a clear departure from normal operating conditions and indicated that heat removal from the affected assemblies was seriously compromised. The high temperature readings demanded immediate operator attention, but the information available in the control room did not clearly indicate the appropriate response or the underlying cause of the thermal problems. The elevated temperatures could potentially have resulted from increased power generation in the affected assemblies, reduced coolant flow, changes in inlet temperature, or combinations of these factors. The neutron flux measurements provided conflicting information about power distribution within the core, and the control system's requirement for additional positive reactivity suggested that overall reactor conditions were changing in ways that were not consistent with simple power distribution variations. At 3:09 p.m., the situation escalated from an operational challenge to a declared radiological emergency when radiation monitors in the building ventilation system detected airborne radioactivity above normal background levels. The radiation alarm provided definitive confirmation that radioactive material had been released from the reactor system, indicating that fuel damage had occurred and that the integrity of fuel pin cladding had been compromised. The detection of airborne activity meant that volatile fission products were being released from damaged fuel and transported through the reactor's cover gas system to the building atmosphere. The containment building isolation system responded automatically to the radiation detection, sealing the reactor building to prevent further release of radioactive material to the environment. This automatic response functioned as designed to limit the consequences of fuel damage, but it also created operational constraints that limited personnel access and complicated efforts to assess reactor conditions. The containment isolation represented the successful operation of one of the reactor's engineered safety features, demonstrating that the defense in-depth safety philosophy was providing protection even though the primary barrier of fuel integrity had been breached. The declaration of a radiological emergency triggered implementation of emergency procedures that required immediate reactor shutdown and protective measures for plant personnel and the surrounding community. Operators terminated the planned power increase and began reducing reactor power towards shutdown conditions, according to established emergency response protocols. However, the emergency procedures had been developed based on anticipated accident scenarios such as loss of coolant circulation or steam generator failures, not the progressive fuel damage scenario that was actually occurring within the reactor core. The reactor power reduction proceeded according to normal shutdown procedures, with power decreasing from the peak level of 31 MWth reached during the event to 26 MWth by 3:20 p.m. At that time, operators initiated manual reactor shutdown by inserting control rods to terminate the nuclear chain reaction and reduce heat generation to decay heat levels. The shutdown process proceeded normally from a control system perspective, with neutron flux decreasing rapidly and reactor power dropping to background levels within minutes of control rod insertion. However, the successful reactor shutdown did not immediately resolve the thermal problems within the affected fuel assemblies because the underlying cause of the overheating remained unchanged. The loose deflector plate that had created the flow blockage continued to obstruct coolant flow to the damaged assemblies, and decay heat continued to be generated within the damaged fuel. Although decay heat generation rates were significantly lower than full power heat generation, the reduced coolant flow meant that even decay heat removal could be problematic in severely blocked assemblies. The physical evidence of fuel damage became apparent through multiple independent indications that confirmed the severity of the event beyond what temperature measurements alone had suggested. The radiation monitors that had triggered the emergency alarm continued to detect elevated levels of airborne radioactivity, indicating ongoing release of fission products from damaged fuel into the reactor's cover gas system. The persistent radiation readings confirmed that fuel pin cladding failures had occurred and that volatile fission products were continuing to escape from the damaged fuel regions. The reactor's cover gas monitoring system provided additional evidence of fuel damage through detection of specific fission product isotopes that could only have originated from within the fuel pins. Noble gas fission products such as xenon and krypton isotopes were detected in concentrations well above normal background levels, providing quantitative evidence of the extent of fuel damage that had occurred. The isotopic signatures in the cover gas samples would eventually allow investigators to estimate the number of fuel pins that had been damaged and the approximate time frame over which the damage had occurred. The sodium coolant system itself became a repository of evidence about fuel damage as fission products released from failed fuel pins were dissolved or suspended in the circulating coolant. The chemical and radiological analysis of coolant samples would eventually provide detailed information about the types and quantities of fission products that had been released, but this analysis required specialized techniques and extended time periods that were not available to operators during the immediate emergency response. The reactor's successful emergency shutdown demonstrated both the effectiveness of its safety systems and the fundamental limitations of its diagnostic capabilities for detecting and preventing the type of failure that had occurred. The containment isolation system had functioned correctly to prevent environmental release of radioactive materials, and the reactor shutdown systems had operated normally to terminate the nuclear chain reaction and reduce heat generation rates. However, the instrumentation and procedures available to operators had proven inadequate for detecting the progressive flow blockage that had caused the fuel damage or for implementing corrective actions before irreversible damage occurred. The physical mechanisms that destroyed fuel within the Fermi 1 reactor core unfolded through a precise sequence of thermal and metallurgical processes that followed predictable physics principles while remaining undetectable through the reactor's available instrumentation until the damage had become irreversible. The fuel destruction resulted from the interaction between reduced coolant flow caused by debris blockage and the continued generation of fission product decay heat within metallic uranium fuel that was not designed to withstand the thermal conditions created by severe flow restriction. The critical failure mechanism occurred when the loose zircaloy deflector plate came to rest in a position that created substantial blockage of coolant flow to specific fuel assemblies. The fuel assembly inlet nozzles were designed as simple cylindrical openings approximately 4 inches in diameter that directed sodium coolant upward through the fuel pin array within each assembly. When the deflector plate, measuring 16 by 8 inches, lodged against or partially covered these inlet nozzles, it reduced the effective flow area available for coolant circulation through the affected assemblies while maintaining normal flow rates through adjacent unblocked assemblies. Under normal operating conditions, each fuel assembly in the Fermi 1 core received sodium coolant at flow rates calculated to remove the heat generated by fission reactions, while maintaining fuel centerline temperatures within design limits established for metallic uranium fuel. The thermal design incorporated safety margins to accommodate reasonable variations in power generation and coolant flow, but these margins assumed that coolant flow reductions would be uniform across the core and associated with overall system transients, rather than localized blockages affecting individual assemblies. When coolant flow to a fuel assembly was reduced by debris blockage while power generation continued at normal rates, the fundamental heat balance within the assembly was disrupted in ways that caused rapid fuel temperature escalation. The heat generation rate within the blocked assembly remained essentially unchanged because neutron flux levels were not significantly affected by the local flow blockage. But the reduced coolant flow was inadequate to remove this heat at the same rate it was being generated. The result was a progressive increase in fuel temperatures that would continue until either additional heat removal capacity became available or the fuel reached temperatures that caused irreversible damage. The thermal response of a blocked fuel assembly followed heat transfer principles that were well understood from reactor safety analysis, but the rate and extent of temperature increase depended critically on the degree of flow obstruction and the specific power generation rate within the affected assembly. Complete blockage of coolant flow would cause fuel temperatures to rise to damaging levels within minutes, while partial blockage would result in more gradual temperature increases that might not immediately exceed fuel damage thresholds but could cause cumulative damage over extended periods. The metallic uranium fuel used in the Fermi 1 reactor had thermal properties that made it particularly vulnerable to damage from overheating, compared to the ceramic uranium dioxide fuels used in most commercial reactors. Metallic uranium has a relatively low melting point of approximately 1,132 degrees, compared to over 2,800 degrees for uranium dioxide, and it undergoes significant thermal expansion and metallurgical changes at temperatures well below its melting point. These characteristics provided excellent neutron economy and heat transfer properties under normal operating conditions, but they also meant that the fuel had limited tolerance for thermal excursions caused by cooling system malfunctions. The fuel pin failure mechanism began when metallic uranium temperatures exceeded design limits and approached the material's phase transition temperatures. As fuel temperatures increased beyond approximately 600 degrees Celsius, the uranium underwent metallurgical phase changes that altered its thermal conductivity, mechanical properties, and dimensional stability. These changes created internal stresses within the fuel pins that were transmitted to the zircaloy cladding tubes that surrounded and contained the fuel material. When fuel temperatures reached critical levels approaching the melting point of metallic uranium, the fuel began to form liquid phases that had significantly different thermal and mechanical properties than the original solid fuel. The molten uranium could not maintain its original geometric configuration within the fuel pins, and it began to redistribute according to gravitational and thermal forces within the fuel pin structure. This fuel relocation changed the spatial distribution of heat generation within the fuel assemblies and created localized hotspots where heat generation exceeded the capacity of the already reduced coolant flow. The failure of fuel pin cladding occurred when the combination of thermal expansion, internal pressure from fuel swelling and gas generation, and mechanical stress from fuel phase changes exceeded the structural capacity of the zircaloy cladding tubes. The cladding was designed to contain solid fuel under normal operating conditions, but it was not intended to withstand the extreme thermal and mechanical loads created by fuel melting and relocation. When cladding integrity was breached, molten fuel and gaseous fission products were released into the sodium coolant stream where they could be transported throughout the primary cooling system. The release of fission products into the sodium coolant created the radioactive signatures that eventually alerted operators to the occurrence of fuel damage, but this detection occurred only after extensive fuel melting had already taken place. The volatile fission products released from failed fuel pins included noble gases such as xenon and krypton isotopes that were relatively inert chemically but could be transported through the sodium system to the reactor's cover gas space where they were detected by radiation monitoring systems. The progression of fuel damage within the affected assemblies followed patterns determined by the neutron flux distribution and heat generation rates within each fuel assembly. Fuel pins located in the central regions of blocked assemblies, where neutron flux and power generation were highest, experienced the most severe overheating, and were typically the first to fail. As these central pins failed and released molten fuel, the thermal conditions within the assembly became increasingly severe, creating a cascade effect that led to failure of additional pins in expanding regions around the initial failure sites. The interaction between molten metallic uranium fuel and sodium coolant created additional complications for heat removal and damage propagation within the affected fuel assemblies. Metallic uranium and sodium can form intermetallic compounds under certain temperature and chemical conditions, and these reaction products have different melting points, thermal conductivities, and flow characteristics than either constituent material alone. The formation of these compounds could potentially create flow blockages within fuel assemblies that would further reduce cooling effectiveness and accelerate fuel damage progression. The neutron physics consequences of fuel damage and relocation created reactivity changes that manifested as the erratic neutron flux readings observed by reactor operators before the extent of fuel damage became apparent through radiation detection. When fuel melted and relocated within fuel assemblies, it changed the geometric arrangement of fissile material within the reactor core, affecting the neutron multiplication characteristics of the system. These reactivity changes required control rod adjustments to maintain desired power levels, creating the condition operators observed where control rods were positioned farther from the core than normal. The reactor's automatic control systems responded appropriately to these reactivity changes by withdrawing control rods to maintain the neutron flux levels called for by the reactor power control system. This control system response was technically correct based on the neutron flux signals it received, but it was compensating for the effects of progressive fuel damage rather than normal reactivity changes associated with temperature variations or operational transients. The control system had no capability to distinguish between reactivity changes caused by fuel damage and those resulting from normal operational factors. The thermal analysis of fuel damage conditions, reconstructed later through detailed forensic investigation, revealed that fuel temperatures in the most severely affected assemblies had exceeded 2,000 degrees in localized regions, well above the melting point of metallic uranium and approaching the melting point of zircaloy cladding material. These extreme temperatures explained the extensive fuel melting and cladding failure that was eventually discovered during post-incident examination of damaged fuel assemblies. The heat transfer analysis demonstrated that adequate cooling could theoretically have been maintained even with significant flow reductions if the blockage had been detected and addressed before fuel temperatures reached damaging levels. The thermal margins incorporated into the reactor design provided some protection against flow reduction, but these margins were based on anticipated transient conditions, rather than sustained blockage of individual fuel assemblies. The analysis showed that early detection and correction of flow blockage could have prevented fuel damage, but the instrumentation available to operators was not capable of detecting localized flow reductions before thermal damage occurred. The mass and energy balance analysis of the fuel damage event revealed the quantities of molten fuel and fission products that were released into the sodium coolant system during the incident. Two adjacent fuel assemblies experienced complete fuel melting in their central regions, with an estimated total of several kilograms of metallic uranium converted to molten form before the reactor was shut down. A third fuel assembly experienced severe overheating with some localized fuel melting, but the majority of fuel pins in this assembly retained their integrity despite exposure to above-normal thermal conditions. The spatial pattern of fuel damage corresponded precisely to the expected consequences of localized flow blockage at specific fuel assembly inlet positions. The fact that damage was concentrated in two adjacent assemblies was consistent with the size and position of the deflector plate debris, which was large enough to simultaneously affect multiple adjacent fuel assembly inlets when positioned appropriately within the reactor's inlet plenum structure. The timeline of fuel damage progression was reconstructed through analysis of the fission product release signatures, detected in the reactor's cover gas and coolant systems. The isotopic composition and decay characteristics of released fission products provided information about when fuel damage began and how rapidly it progressed during the final hours before reactor shutdown. This forensic analysis indicated that significant fuel damage had been occurring for several hours before radiation detection systems provided clear indication of the problem to reactor operators. The failure chain analysis revealed how multiple physical processes interacted to create consequences that exceeded the effectiveness of individual protection systems designed to prevent fuel damage. The reactor's thermal design margins, control system responses, and emergency detection systems were all appropriate for the individual challenges they were designed to address, but their combined effectiveness was insufficient to prevent core damage when the fundamental assumption of adequate coolant flow was violated by an unanticipated debris blockage mechanism. The physics of the failure progression demonstrated the importance of early detection capabilities for preventing cascading failures in complex technical systems. Once fuel temperatures exceeded critical thresholds, the physical processes of melting, relocation, and fission product release became self-reinforcing in ways that made recovery increasingly difficult, regardless of subsequent operator actions or system responses. The point of no return was determined not by control system capabilities or emergency procedures, but by fundamental materials science limits on fuel integrity under severe thermal conditions. 8:20 p.m. The stabilization of the Fermi 1 reactor following the fuel damage event required operators and engineering personnel to manage a complex array of technical challenges while operating with fundamental uncertainty about the extent of damage within the reactor core and the continued presence of debris that could create additional flow blockages. The successful reactor shutdown had terminated the nuclear chain reaction and reduced heat generation to decay heat levels, but it had not addressed the root cause of the fuel damage or provided assurance that the reactor system was in a stable, safe configuration for extended shutdown periods. The immediate priority following reactor shutdown was establishing and maintaining adequate decay heat removal from the damaged fuel assemblies while preventing further fuel damage that could occur if cooling continued to be inadequate. Although the nuclear fission process had been terminated by control rod insertion, the damaged fuel continued to generate heat from radioactive decay of fission products at rates that initially amounted to approximately 6% of the reactor's full power thermal output. This decay heat would decrease exponentially with time according to well-established physical principles, but it remained sufficient to cause additional fuel damage if adequate cooling was not maintained. The challenge of ensuring adequate decay heat removal was complicated by fundamental uncertainty about the condition of fuel assemblies throughout the reactor core, and the continued effectiveness of coolant circulation through potentially blocked or damaged fuel channels. The loose deflector plate that had initiated the fuel damage remained somewhere within the reactor system, with its location and orientation unknown to operators or engineering personnel. The plate retained the potential to shift to new positions and create additional flow blockages, possibly affecting fuel assemblies that had not been damaged during the initial event. The reactor's primary sodium circulation system continued to operate following shutdown, with circulation pumps maintaining coolant flow through the reactor core at reduced rates appropriate for decay heat removal conditions. The continued operation of the circulation system was essential for preventing additional fuel damage, but the presence of fission products in the sodium coolant created new operational challenges related to radiation protection, system chemistry control, and long-term equipment reliability. The molten fuel that had been released from failed fuel pins had introduced materials into the coolant system that could potentially affect pump operation, heat exchanger performance, or the chemical balance of the sodium coolant. Radiation monitoring throughout the reactor facility indicated that significant quantities of fission products had been released into the sodium coolant system, but the chemical form, distribution, and transport behavior of these materials within the circulating coolant was not immediately determinable through available monitoring systems. Some fission products remained dissolved in the sodium coolant and were transported throughout the primary circulation loop, while others might precipitate onto system surfaces or accumulate in regions of low coolant velocity, such as heat exchanger tubes or piping dead legs. The reactor's cover gas system provided continuous monitoring of volatile fission products that were released from damaged fuel and transported to the argon atmosphere maintained above the sodium coolant surface. This monitoring capability offered important information about the continuing rate of fission product release from damaged fuel, which could indicate whether additional fuel damage was occurring, or whether the release rate was decreasing consistent with successful stabilization of thermal conditions within the core. The cover gas monitoring data indicated that fission product release rates had decreased significantly following reactor shutdown, suggesting that the termination of nuclear fission and reduction in heat generation rates had stabilized thermal conditions sufficiently to prevent continuing fuel damage. However, the monitoring also showed that fission product release continued at levels well above normal background, confirming that damaged fuel remained in contact with the sodium coolant and that some degree of ongoing interaction between damaged fuel materials and the coolant system was continuing. The containment building isolation that had been automatically implemented following detection of airborne radioactivity remained in effect during the initial stabilization period, successfully preventing any release of radioactive materials to the environment while creating operational constraints that limited personnel access and equipment maintenance activities. The containment isolation systems had functioned exactly as designed to limit the consequences of fuel damage, demonstrating the effectiveness of engineered safety features, even when primary fuel integrity barriers had been breached. The reactor's instrumentation systems continued to provide information about key system parameters, but the interpretation of instrument readings was complicated by the changed conditions within the reactor core and primary coolant system. Fuel assembly outlet thermocouple readings provided indication of coolant temperatures, but they could not definitively distinguish between normal decay heat removal and continued thermal problems in damaged assemblies. The presence of fission products in the coolant and potential changes in flow distribution meant that temperature readings might not accurately reflect thermal conditions within fuel assemblies. Neutron monitoring systems confirmed that the reactor remained safely subcritical with adequate shutdown margin provided by the inserted control rods, but these measurements provided no information about the physical condition of fuel within the core or the effectiveness of cooling in potentially damaged regions. The neutron detectors could verify that no significant nuclear chain reaction was occurring, but they could not detect localized thermal conditions that might lead to additional fuel damage from inadequate decay heat removal. The plant's emergency response organization implemented comprehensive procedures for managing the radiological consequences of the fuel damage event, while maintaining essential plant systems and preparing for the extended investigation that would be required to understand the cause and extent of the incident. Emergency procedures were adapted to address the specific conditions created by fuel damage in a sodium-cooled reactor, including enhanced radiation protection measures, specialized contamination control protocols, and modified system operation procedures to accommodate the presence of fission products in the primary coolant. The engineering analysis of post-shutdown conditions focused on confirming through calculation and analysis that adequate cooling capacity existed to maintain fuel temperatures within acceptable limits, even if some degree of flow blockage continued to affect individual fuel assemblies. These thermal analysis calculations required assumptions about fuel condition, coolant flow distribution, and heat generation rates that could not be verified without direct examination of reactor internals, but they provided conservative estimates of cooling requirements and safety margins under various postulated conditions. The decision-making process for long-term reactor stabilization and incident investigation required extensive coordination between reactor operations personnel, plant engineering staff, corporate management, regulatory authorities, and external technical consultants with specialized expertise in fast reactor technology and fuel damage analysis. The unprecedented nature of significant fuel damage in a commercial sodium-cooled reactor meant that established procedures and industry precedents provided limited guidance for managing the complex technical, regulatory, and public relations challenges associated with the incident. Technical decisions regarding reactor system operation, investigation planning, and recovery strategies had to be made based on engineering judgment, conservative safety analysis, and limited precedent from research reactor incidents rather than definitive knowledge about fuel and system conditions. The opacity of liquid sodium coolant meant that direct visual assessment of core conditions was impossible, and the high radiation levels within the reactor system precluded personnel access for hands-on inspection or repair activities. The development of plans for investigating the root cause and extent of fuel damage revealed significant limitations in existing technology and procedures for examining reactor internals in a highly radioactive sodium environment. Conventional inspection techniques used in water-cooled reactors were not applicable to sodium systems, and specialized equipment would need to be designed, fabricated, and tested before definitive information about fuel condition and the location of debris could be obtained. The reactor remained in a stable shutdown condition throughout the weeks immediately following the October 5 incident, with primary circulation systems maintaining adequate coolant flow and decay heat removal systems preventing additional fuel damage. Radiation levels within the plant remained elevated but stable, and containment systems continued to prevent any release of radioactive materials to the environment. However, this apparent operational stability masked fundamental uncertainties about the condition of reactor internals and the measures that would be required to address the root cause of the fuel damage. The gradual decrease in decay heat generation over time reduced thermal stress on damaged fuel assemblies and decreased the immediate risk of additional fuel damage, but it did not resolve the underlying flow blockage problem or provide confidence that the reactor could eventually be returned to safe operation. The loose deflector plate remained within the reactor system as a continuing potential source of flow blockages, and the damaged fuel assemblies would require removal and replacement before normal reactor operation could be resumed. Secondary challenges emerged from the presence of fission products throughout the primary sodium system, creating contamination that complicated maintenance activities and required specialized procedures for any work involving primary system components. The long-lived radioactive isotopes in the released fission products meant that elevated radiation levels would persist within the primary system for months or years, affecting all subsequent inspection, maintenance, and repair activities. The stabilization period demonstrated both the robust effectiveness of the reactor's engineered safety systems in limiting the consequences of core damage and the significant challenges associated with investigating and recovering from complex failure modes in experimental reactor designs. The containment systems had successfully prevented environmental release of radioactive materials despite extensive fuel damage within the core, and the reactor cooling systems had maintained adequate heat removal to prevent escalation to more severe damage conditions. However, the technical challenges associated with proving the cause of the incident and demonstrating the safety of continued operation remained formidable. The investigation would require the development of new remote examination techniques, the design and fabrication of specialized handling equipment capable of operating in highly radioactive sodium environments, and the implementation of extensive fuel handling and replacement operations under unprecedented radiological conditions. The lessons learned during the initial stabilization period would significantly influence subsequent investigation and recovery efforts, highlighting the critical importance of comprehensive diagnostic capabilities, robust emergency response procedures, and adequate technical resources for managing unprecedented events in complex reactor systems. The incident had revealed important gaps in the understanding of potential failure modes and the adequacy of existing procedures for diagnosing and responding to fuel damage in sodium-cooled reactor systems. The forensic investigation of the Fermi 1 fuel damage incident required the development of entirely new technical capabilities for examining reactor internals in a highly radioactive liquid sodium environment, representing one of the most challenging engineering investigations ever undertaken in the commercial nuclear industry. Over more than a year following the October 5, 1966 event, investigators employed increasingly sophisticated remote examination techniques to penetrate the diagnostic opacity that had prevented detection of the failure mechanism during its development and to establish definitively what had occurred within the reactor core. The initial phase of the forensic investigation relied on indirect evidence obtained through systematic analysis of reactor system parameters, coolant chemistry measurements, and radiation monitoring data to characterize the nature and extent of fuel damage that had occurred. Sodium coolant samples were extracted from the primary circulation system and subjected to detailed radiochemical analysis to identify the types and quantities of fission products that had been released from damaged fuel pins. These analyses revealed the presence of volatile fission products, including cesium, iodine, and noble gas isotopes, as well as less volatile species that indicated extensive high-temperature interaction between fuel materials and the sodium coolant. Cover gas samples from the argon atmosphere maintained above the sodium coolant provided additional forensic evidence about the fuel damage through detection and analysis of gaseous fission products that had been released from breached fuel pin cladding. The isotopic composition and activity levels of noble gases, such as xenon and krypton, allowed investigators to estimate the approximate number of fuel pins that had experienced cladding failure and to determine the general time frame over which the damage had occurred based on the decay characteristics of short-lived isotopes. However, these indirect analytical techniques could not provide the definitive physical evidence required to prove the specific mechanism that had caused the fuel damage or to locate the debris that had created the flow blockage conditions. The forensic investigation required direct visual examination of reactor internals, which presented unprecedented technical challenges due to the complete opacity of liquid sodium to visible light, the high operating temperatures of the sodium system, and the intense radiation fields created by fission products distributed throughout the primary coolant. The technical obstacles to direct examination of reactor internals in the sodium environment were unlike anything previously encountered in nuclear facility investigations. Conventional underwater inspection techniques used in water-cooled reactors were completely inapplicable to liquid sodium systems, and no existing technology provided the capability for remote visual inspection in opaque, high-temperature, chemically reactive liquid metal environments. The development of appropriate examination tools would require fundamental advances in remote handling technology, materials science, and optical systems design. The solution developed through collaboration between reactor engineering staff and specialized equipment manufacturers involved a combination of mechanical probing systems, ultrasonic examination techniques, and innovative optical devices specifically designed for operation in liquid sodium environments. The remote examination system incorporated a manipulator arm capable of being inserted through existing reactor vessel access ports and positioned to examine specific areas of interest within the reactor internals with sufficient mechanical dexterity to retrieve small objects and adequate structural strength to operate reliably in the challenging thermal and chemical environment. The first breakthrough in the forensic investigation occurred during systematic examination of the reactor's inlet plenum region beneath the core support structure, where investigators detected a foreign object that did not correspond to any component shown in the reactor's design documentation. The object's location, size, and geometric characteristics were consistent with a deflector plate that had broken loose from its original mounting position, providing the first direct physical evidence of the mechanism that had caused the fuel damage. The identification of debris within the inlet plenum confirmed the hypothesis that flow blockage had been responsible for the fuel overheating, but recovery of the object for detailed examination required additional development of specialized remote handling equipment. The loose deflector plate had become wedged in a position that made extraction technically challenging without risking damage to adjacent reactor components or creating additional debris that might complicate future operations. The debris recovery operation required precise manipulation of remote handling tools while working through several feet of liquid sodium and navigating around reactor internal structures with limited visibility and restricted access. The recovery tools had to be designed with sufficient gripping capability to securely hold the deflector plate while having small enough dimensions to fit through the available access routes within the reactor vessel. The operation was further complicated by the need to avoid any actions that might damage fuel assemblies or create additional loose debris within the reactor system. When the deflector plate was successfully recovered and removed from the reactor system, physical examination confirmed that it was indeed one of the 6 plates that had been installed during reactor construction to optimize sodium flow distribution through the core. The plate showed clear evidence of having been subjected to the high-temperature sodium environment, with surface oxidation and some deformation consistent with extended exposure to flowing coolant and thermal cycling during reactor operation. Detailed metallurgical analysis of the recovered deflector plate and examination of fragments of its original mounting hardware revealed that failure had occurred due to fatigue cracking in the weld attachments that had secured the plate to reactor internal support structures. The fatigue mechanism was determined to have resulted from the combination of thermal cycling stresses imposed during reactor startup and shutdown operations and flow-induced vibration caused by sodium circulation around the plate during normal operation. The failure analysis demonstrated that the weld fatigue was a predictable consequence of the thermal and mechanical loading conditions that the mounting system had experienced during reactor operation, rather than a random material defect or unusual service condition. The mounting welds had been subjected to thermal expansion and contraction stresses during each reactor thermal cycle, and these stresses were concentrated at the weld interface where material properties and geometric configuration created stress concentration factors that accelerated fatigue crack initiation and growth. The forensic examination of damaged fuel assemblies required development of additional specialized techniques for fuel handling and disassembly under conditions that prevented spread of radioactive contamination while preserving the metallurgical evidence needed for detailed failure analysis. Individual fuel assemblies had to be removed from the reactor core using remote handling equipment specifically designed for highly radioactive components, transported to shielded examination facilities, and systematically disassembled to allow inspection of individual fuel pins and assessment of damage patterns. The detailed fuel examination revealed the extent and progression of fuel damage with unprecedented precision, providing definitive confirmation of the thermal mechanisms that had caused fuel failure. 2 adjacent fuel assemblies had experienced complete fuel melting in their central regions, with metallic uranium forming resolidified masses that preserved a detailed record of the thermal and hydraulic conditions that had existed during the melting process. The solidified fuel formations showed clear evidence of having reached temperatures well above the melting point of uranium metal, with microstructural features indicating peak temperatures had exceeded 2,000 degrees Celsius in localized regions. A third fuel assembly showed evidence of severe thermal exposure with extensive fuel pin damage but no complete fuel melting, indicating that it had experienced significant flow blockage for a shorter duration or to a lesser degree than the 2 assemblies with complete fuel melting. The damage pattern within this assembly was consistent with partial flow blockage that had caused fuel temperatures to approach but not exceed the melting point of metallic uranium, before reactor shutdown terminated heat generation and allowed thermal recovery. The metallurgical analysis of failed fuel pins provided conclusive evidence of the failure mechanisms and thermal history of the fuel damage event. The progression of fuel heating, phase changes, melting, and interaction with zircaloy cladding materials could be reconstructed from microstructural examination of the solidified fuel masses and analysis of the chemical compounds formed during high-temperature interaction between fuel and cladding materials. The spatial distribution of fuel damage within affected assemblies corresponded exactly to the anticipated consequences of coolant flow blockage at fuel assembly inlets, with the most severe damage occurring in fuel pins located in the central regions where neutron flux and heat generation rates were highest. Fuel pins near the periphery of blocked assemblies, where heat generation was lower and some residual coolant flow may have been maintained around the edges of the flow blockage, showed progressively less severe damage with increasing distance from the assembly centerline. The forensic findings were documented in comprehensive technical reports that provided the nuclear industry with its first detailed analysis of fuel damage mechanisms in sodium-cooled fast breeder reactors and established definitive precedents for investigating similar events in liquid metal reactor systems. The investigation reports included complete metallurgical analysis results, thermal analysis calculations that reconstructed the temperature history of damaged fuel, and forensic timeline reconstructions that demonstrated the sequence of events leading to fuel damage. The regulatory response to the Fermi 1 investigation findings resulted in fundamental changes to fast reactor design requirements and licensing procedures that were implemented to prevent similar incidents in future reactor designs. New regulations required that reactor designs demonstrate immunity to flow blockage caused by debris generation from any single component failure and that adequate monitoring capabilities be provided to detect developing flow problems before fuel damage could occur. Enhanced debris monitoring systems were mandated for future fast reactor designs, incorporating multiple independent measurement techniques to detect foreign objects in reactor coolant systems before they could cause significant flow blockages. Improved fuel assembly instrumentation requirements included more sensitive temperature monitoring and flow measurement capabilities that could provide early warning of developing thermal problems in individual fuel assemblies. The technical legacy of the Fermi 1 forensic investigation extended throughout the nuclear industry, influencing approaches to failure analysis, remote inspection techniques, and emergency response procedures for reactor incidents involving inaccessible damage in challenging environments. The investigation demonstrated the feasibility of conducting comprehensive forensic analysis, even under extremely difficult technical conditions, while also revealing the time, cost, and technical resource requirements associated with such investigations. The successful completion of the forensic investigation and the reactor's eventual return to operation with a redesigned core using uranium dioxide fuel validated the effectiveness of systematic engineering analysis in understanding complex technical failures and developing appropriate corrective measures. The detailed knowledge of fuel damage mechanisms gained through the investigation provided the technical foundation for improved reactor designs and enhanced safety analysis methods that reduce the probability of similar events in subsequent reactor systems. The Fermi 1 incident ultimately demonstrated both the challenges and capabilities of 1960s nuclear technology in managing unprecedented technical failures. The reactor's engineered safety systems had successfully limited the consequences of fuel damage, preventing environmental release of radioactive materials despite extensive core damage. The forensic investigation had proved that even novel and complex failure modes could be understood through systematic application of engineering analysis and specialized experimental techniques, providing the knowledge needed to prevent recurrence through improved design and operation practices.